All right, so we're going to learn these different identities. We have 3 classes of them, or 3 categories. Again, we know most of them, and the ultimate goal is to solve trig equations, which we'll do later this week. And so one such identity we see at the bottom, we know that 1 divided by the cosine of an angle, like if you saw that written down, 1 divided by the cosine, you know that you could also just take the secant of that angle and you'd get the exact same value. Can you think of any other identities off the top of your head that you already know, possibly? What's that? Cosecant. Yeah, what's cosecant equal? 1 over the sine. Yeah, that's another identity. And we have special names for those. These are the reciprocal identities, because remember how the reciprocal just means you flip the fraction? So you can jot these down if you want. You might want to have a special box for them. But you should know all these already. You've seen all these earlier in this unit, right? You've seen secant is 1 over cosine, right? We learned that, before spring break. That was over a month ago. Or one's like, hey, tangent is 1 over the cotangent. Okay, these are reciprocals. So these are the 6 reciprocal identities, meaning if I take any of those 6 trig functions and flip them upside down or write them as 1 over that trig function, that creates another trig function that has its own name. And so the first reciprocal identities that you learned this year were the secant, cosecant, and cotangent. Now, these are pretty similar. You don't have to, hopefully you still remember these. I mean, you had to use this on your most recent test using the unit circle for exact trig values. But see how I've grouped them together? I've got, here's secant and cosine. Well, here's cosine and secant, right? They're just reciprocals of each other. So it's not like 6 completely separate, unrelated identities. And so the idea is if you ever see a problem written one of these ways with like a 1 over a trig function, we know we can just rewrite it as a separate trig function, which should make it simpler and easier. Maybe cancel some stuff out so that we can easily solve these trig equations later on in the week. So then you got cosecant and sine, and you got tangent and cotangent. Remember the way to keep those straight? First, tangent and cotangent are just reciprocals of each other because they both have the word tangent in them. As far as secant, cosecant, sine, and cosine are concerned, the way I keep them straight is all 4 of those start with either a C or an S. And I always just try to keep it straight by remembering if your basic function starts with an S, its reciprocal will start with a C. You change that first letter from C to S or S to C, because like the reciprocal is like flipping it. So I kind of think in my head, all right, if I had a C, I'm going to flip it, and now I have an S trig function. So you wouldn't have like a cosine and a cosecant because those both start with C. It doesn't work that way. Anyways, that's just my little trick that I use. You might have your own way for remembering the difference between these two. All right, so those are these 6 reciprocal functions. Remember, we're going to learn 3 different groupings of identities today. This is just the first one. But let's look at how we would use this, how this would apply to simplifying a problem. Oh, these 2 quotient identities, we've kind of saw this on the unit circle. Whenever we ask for like the tangent of an angle, we'd say, oh, that's y over x. But isn't sine the y and cosine is the x? So this is another way that we can rewrite or simplify 2 functions. If we have an expression that said, hey, take the sine of an angle and divide it by the cosine of an angle, instead of doing those 2 calculations, we could do just a single calculation of tangent. It's the same thing. So this is called an identity because they're equal to each other. That's what the equal sign means. It means the left side is exactly the same as the right side. And so tangent is sine over cosine. Cotangent is cosine over sine. Best way to keep these straight, cotangent starts with cosine in the numerator. They both have that co to lead things off. So cotangent equals cosine over sine. And so again, just imagine you've got an expression or an equation with some of these trig functions with a bunch of different trig functions here, like a cosine divided by a sine. And instead of writing that, you can take that out and just put in a cotangent. It's simplified. It's fewer functions. It's less work you have to do. But these are called the quotient identities because quotient simply means division. And so you can see that these are being divided, right? Cosine divided by sine or sine divided by cosine. Their quotient is either the tangent or the cotangent. Yeah. Oh, yeah. Yeah, no, that is a really good idea. Like if I had sine, like if I multiplied both sides by cosine, these would cancel out. Is that what you're saying? So then like the cosine of x times the tangent of x equals sine? No.
They do not have like tangent in the others. Like so it'd be like cosine equals sine over like tangent or no. Like it's like you know.
Do you want to come show me what you mean?
Okay.
Yeah, you can do this. Come on up.
No, it's a really stupid question. Okay. I was saying like could you put like this is here and this is here?
Oh, yes.
You can? Okay. That was my question.
Yeah, just like any other, because like if I multiplied both sides of this, that makes it a little smaller, so I have room to work with. All right, so you're saying, can I swap those two essentially? And yes, you can, and that would still be considered an identity. And what you'd actually be doing is multiplying both sides by sine first, taking it one step at a time. So that'd give me sine times cotangent equals cosine, right? If I multiplied both sides by sine. And then if I want to get the sine by itself, I would divide by cotangent. So those would cancel out. And then essentially that would result in the swap, right? I'd have sine equals cosine over cotangent. So like we saw that sometimes when we were solving for just a basic sine or cosine of like a right triangle, and if like the variable was in the denominator, we would just do that swap. Same kind of a move. We're actually doing two different algebraic steps, but you're in algebra 2. You can go ahead and just take that shortcut and just swap them right away. We understand that, okay, I'm actually multiplying both sides, then dividing both sides using our equivalence properties of algebra. We're allowed to do that. Absolutely. So here's what I mean by simplifying trig expressions. If I gave you a problem that said, hey, take the cotangent of an angle and divide it by the cosine of an angle. Well, that's going to be two different calculations. Actually, three, because I have to find the cotangent of the angle, then the cosine of the angle, then I have to divide them, right? There's like three steps right there. What if instead I simplified this, said it was just a single trig function? And that's our goal, to make less work for ourselves in the long run if we recognize some of these identities. And so what you want to do, and this is going to be where some of these identities are going to be kind of like a puzzle, whereas you're not really sure what's the correct first step. It's not going to be, hey, you always do this first, you always do that first. It's going to depend on the problem that you're given. What you know is kind of frustrating because you like to be like, oh, I do this first and this first and this first, and I get the answer. Unfortunately, that's not going to be the case here. You have to try some things, and you might not get it the first time, then you have to start over and try simplifying it a different way. Because I can replace these, and you see as we get more and more identities, there's a bunch of different ways that we could substitute some of these out and see what we get. But a good general way to start, I'm going to recommend to you and try to encourage you to always do, is if you've got some combination of trig functions, try rewriting all of them in terms of sine and cosine. Now up there, I have two trig functions right now separately. Yeah, they're being divided, but don't worry about that. We can treat like the numerator and denominator as two separate things for now. And there's a cotangent on top and a cosine on the bottom. So if you want, we can think of this as the cotangent times 1 divided by the cosine. Would you all agree that these are the same thing? Right? Dividing by the cosine is the same as just multiplying by 1 over the cosine. It's kind of like if I took divided by cosine of x, it's almost as if I took this quotient and I separated it out, right? Like I moved it over to the side. It's kind of like I just slid it over there, but it's still in the denominator. So I still have to make it 1 over cosine. It's not cotangent times cosine, but it's almost like I took that fraction, its top and bottom, and I separated them out. I just slid them to the side, and I'm viewing them as two separate functions. So what we've got now is just a cotangent, that is an S, times 1 over the cosine of x. So just view them as two separate terms that you're going to be multiplying together. And you want to write each of those in terms of sine and cosine. Now, the one on the right is already in terms of cosine, right? You have 1 over the cosine. Go ahead and leave that there because it's already a cosine. What I'd want to do is change this cotangent. So think about those identities, the reciprocal identities and the quotient identities. And if I go back to this slide, we see that, hey, cotangent, I know that one. It's right here. And cotangent is 1 over tangent. I could replace the cotangent of x with 1 over the tangent. But if I did that, it wouldn't really help me in this problem because then I'd have 1 over the tangent times 1 over the cosine. Now, is that simplified at all? Does that help me cancel things out? Do I have fewer trig functions? No, not at all. And that's why my recommendation was to write things in terms of sine and cosine. So we have a different identity that we would want to use in this case for cotangent. Look at these quotient identities. We see here, hey, cotangent is the same thing as the cosine divided by the sine. Now that looks a little bit better because it's got cosine and sine. I know I already have a cosine in my problem. Maybe they'll combine somehow or cancel out or something like that. So what I'm going to do is take this problem here. Let me clean this up. So we've got our cotangent. I keep on doing that. So take your cotangent of x times 1 over cosine. And I'm going to replace cotangent with its quotient identity, with cosine divided by sine. So I'm going to rewrite this problem. But instead of writing cotangent, so instead of writing this, I'm going to write what it's equal to, which is the cosine divided by the sine. All right, now it's still being multiplied by 1 over the cosine of x. All right, so all I did is I replaced that cotangent trig function with a cosine divided by sine. I still have this combination of multiple trig functions here. Now it looks like I've got even more. I've got 3 trig functions. But can I simplify something in there now really nicely? If I look at both of those fractions that are being multiplied, what can we do now? Yeah. Remember, if you're multiplying 2 fractions, essentially you treat it as like one giant fraction. And look at all the numerators and all the denominators. And now I see, hey, there's a cosine on the top and a cosine on the bottom. Well, if I multiply something by cosine and then I divide by something by a cosine, it's as if I didn't do anything at all with those cosines because cosine divided by cosine is 1. It cancels out. So this is essentially, well, let's see what I have left over. In the numerator, all I have left is a 1. In the denominator, all I have left is a sine. Okay, well, that does look simplified. I started out with 2 trig functions. Now I only have 1. This is great. This is definitely simpler than that. But there's still this division. I still would have to calculate the sine of x and then take 1 divided by that number. There's one last thing I could do to make this even simpler. What do you think that would be? Yeah, 1 over sine. I've seen that before also. Go 2 slides back. And if we look right here, 1 over sine. I've seen that in one of my identities. 1 divided by sine, that's a reciprocal, so that's going to be one of my reciprocal identities. That's the same thing as just the cosecant of x. So I'm going to go back to my problem here, to my 1 divided by sine. I'm saying, oh, that's the same thing as just the cosecant of x. And so I took that original problem with 2 different trig functions, and now it's simply the cosecant of x. It's one single trig function. This looks much simpler than this original problem was up here, but they're still equivalent because we use these identities to substitute equal things out. Gavin?
So, for cotangent, just say like it's the cosine of like 52. Would both like this is the cosec and the sine both get 52?
That's right. Notice how I keep using x everywhere. X is one number. Or if I use theta or y, whatever the variable is, you'd be using that same one. So the cotangent of 50 degrees divided by the cosine of 50 degrees is the same thing as the cosecant of 50 degrees. They would all result in the exact same decimal, basically, whatever that number is. And so yeah, you see that there's whatever this x is, this would have to be that exact same variable. Whatever number you plugged in for x, it's the same throughout. Same thing with down here. All right, so that's simplifying these trig functions by using these identities. All right, I want you to try to do this one on your own, everybody. The sine of an angle times the secant of an angle. Can you simplify that until it's a single trig function? So right now there's 2 trig functions. Write that as a single trig function without a denominator. All right, so you don't want to have a fraction, just like that last one when we had 1 over sine, we rewrote that as just cosecant. So look at your identities. Come on. Look at those identities that you wrote down at the start of the lesson and see what can you substitute one of these with. Remember, my first recommendation to you is to always just try write everything in terms of sine and cosine and see what happens. So this is a sine already. This isn't. How would you rewrite this in terms of just a sine or a cosine or some combination? Look up here and see what you could do, what you could replace it with. Okay, now if you were to multiply these together, what would that fraction look like? So now if you were to multiply these together, what would that new fraction look like? Make it into a single fraction. Yes. Yes. Look, do you have those identities written down?
No, I assume.
So when I put that on the board and said, hey, write these down, these are important. And then I didn't do anything for like 4.5 minutes to give you time to write.
I assumed it was, I didn't look at them, but I never realized.
Yeah. Mm-hmm. All right, so if I want to write this in terms of sine and cosine, first, sine is good. I think I'll leave that as just a sine. But secant, Well, I know that that's one of these newer identities. That's one of the reciprocal identities. And I can rewrite that as 1 over the, and I know if you forget what it is, remember, if that started with an S, its reciprocal should start with a C. So that's a cosine of x. All right, so now I only have sine and cosine. What do I do from here? Well, right now, we can think of this as one fraction being multiplied by another fraction. What happens if we combine that? Right, for multiplying, I can always treat this as like a single fraction bar. Well, let's rewrite that. So I have sine of an angle divided by the cosine of an angle. And again, we're just trying things. This might not work. All right, I'm giving you some basic ones today, but sometimes you're going to substitute something in, you're going to simplify, you're going to combine it, and you're like, I don't see any other identity. This might not work. You might have to start over, and that's okay. But right now, we just multiply these, and we're like, okay, so now I've got a fraction of sine divided by cosine. Great. It's still in terms of sine and cosine. I still have 2 trig functions, though. But hopefully you recognize this as one of our quotient identities. Sine divided by cosine, that's simply the tangent of an angle. So the sine of whatever angle times the secant of that same angle, instead of doing 2 separate calculations and then multiplying them, I could just simply take the tangent of that angle and I'd get the same exact answer. So this is a much simplified calculation that I could do. How many of you did get tangent, by the way? I saw a good number of you. Awesome. All right, so that's your first focus, is to try to recognize these and just replace them. Sometimes, if we're multiplying the same trig function times itself, it can look a little different. So what we have to do, if I had sine times sine, here, let me show you this first. Here's the problem we get. If I'm multiplying sine times another sine, how do we usually write that simplified? Yeah, when we write the exponent of a 2. But here's the problem. If I write sine of x squared, this is a bit ambiguous, meaning it's not clear exactly as to what's being squared. Because x is a number, but sine of x is a different number, right? That'd be some different decimal. Like if x were 30 degrees, the sine of 30 degrees is something completely different. And so it's like, I don't know, is this saying, and that's what I'm showing here. See how this shows that, oh no, take the sine of x first, like in your calculator, take the sine of x, hit enter, get that number, and then square that number, as opposed to this might look like the sine of x squared. It's not intentionally clear as to, wait, am I squaring x first and then taking the sine? Or do I take the sine of x first and then square it? It can get pretty confusing that way if we left the exponent just hanging out up here in the upper right. So to avoid that confusion, first off, just in general, we're never going to typically square the angle inside. All right, for this unit, for this year, for most of trigonometry, you never really square the angle. It's always the entire trig function that you're going to have squared, right? This entire, take the sine of x, hit enter, get that value, and then square it. So the way that you're going to see this written is we simply move the exponent from after the x to right here. Do you see how it's after the sine? That's indicating, hey, I'm squaring the sine of this angle. I'm not squaring the angle itself. So x isn't being squared, but the sine of x is being squared. And so if you ever see that here, I know it's kind of weird because like the sine and the x are together. They're one single value, one single operation. But we have to move that 2 in front of it. So it's going to be the sine squared of x. Simply means I've got 2 of these, right? The sine of x times another sine of x. It's just we write the exponent after the sine, not after the x. So make a note of that. That this equals this. So that if we ever do see something squared, cosecant squared of x, that means the cosecant times another cosecant. It's not the angle that's being squared. It's not going to be an x times another x. It'll be the function times another of those same functions. Now, if you do have a squared function like this, see how these both have the exponent written in between the trig function and the x? That just means I've got like two cosecants being multiplied and two tangents being multiplied. The nice thing is all those rules, all those identities that we looked at before for like 1 over sine or cosine divided by sine, if the function is squared, they still work exactly the same. And so rewriting any of these squared functions works the same as rewriting a non-squared trig function. So like on the left here, I've got a cosecant squared of x. Now remember, my first rule to you was always see if you can rewrite things in terms of sine and cosine. So let's take a look at this cosecant. How would I rewrite the cosecant? Good, 1 over sine. Now because this is the cosecant squared, all we would write is 1 over sine squared of x. Okay, even though it's squared, it's still 1 over sine, but since it's cosecant squared, it's just 1 over sine squared. So you just bring the exponent along for the ride. Times. Now look at the second trig function, tangent squared. Can we rewrite tangent in terms of sine and cosine? What is it? What's it going to be?
Sine over cosine.
Good. Now, because it's tangent squared, we're just going to make both of those, the sine and cosine, squared as well. You just bring that exponent along for the ride. So that's sine squared over cosine squared. All right, so it really doesn't change any of the behaviors of these identities if one of them is being squared or cubed or to the fourth power or any other exponent. You bring that same exponent along. Now looking at this right here, it's multiplying two fractions. I'm going to treat it as one fraction. What can we cancel out? I've got the sine squared up top and a sine squared in the bottom, right? It's almost like I've got sine times sine in the numerator and another sine times sine in the denominator. They're both going to cancel out. That leaves me with just a 1 in the numerator and a cosine squared in the denominator. All right, I've got 1 over cosine squared. Well, think, we have an identity for 1 over cosine, don't we? What is that? That's the secant. And since it's being squared, we would just write this as the secant squared of x. And so that square just kind of comes along. It doesn't change the functionality of these for substituting in these equivalent identities. Anyone get that secant squared? Did you like work ahead and figure that? That's awesome. Any questions so far? And where I got some of these values from that I'm rewriting them as. All right. Go ahead and try this one on your own. Let me make that a little bit bigger for you. Ooh, 3 trig functions. All right, so you've got the sine squared times the cotangent times the secant. Rewrite that out. And I want you to try to simplify that into a single trig function. No denominators, just a single trig function for a single calculation. So go ahead, I take each one of those and try rewriting them in terms of sine and cosine. Okay, that was scary fast. These are kind of fun, aren't they? Sorry. What do you think it is?
I think that when you put it all together, it just equals sine.
Get it? Yeah, nice job. Exactly. 2 on top, 1 on the bottom. Just like if I had x squared over a single x, right? Isn't there one of each of these cancels and you're left with 1 up top? Because again, you could rewrite that as sine times another sine if you wanted to. So one of those would cancel, but there's still another one up there that would still remain. What? It's too easy. Yes. So nice when everything just falls into place. So for this middle one, for cotangent, instead of rewriting it as 1 over tangent, just write this in terms of sine and cosine. Remember those 2 quotient identities? Use that instead. So always try to put everything in terms of sine and cosine first. So you want to try to think of keeping everything in terms of sine and cosine. So this first one, whoops. Where, what? What is going on? Why is this over here now? Oh my gosh. So look at each of these 3 separate trig functions. The first one is already in terms of a sine or a cosine. So we want to leave that alone. Don't rewrite it as anything else. Just keep this as sine squared. The second one, cotangent. Well, for this, I've got 2 options. I could rewrite it as 1 over tangent, but that's not going to help me because that's still not in terms of sine and cosine. Typically, I'd only use the tangent and cotangent reciprocal if I've got all tangents and cotangents in my function, because then I know like a tangent could cancel out with a cotangent because they're reciprocals and they would cancel one another out. But if you only see just one of them there, I would always say try putting everything in terms of that sine and cosine first. That's usually going to be your best bet. And cotangent is the same as cosine. Remember, they both start with the co divided by sine. Last, I've got the secant. All right, so secant, that's one of those reciprocal identities. That's going to be 1 over the, and since this started with an S, it's reciprocal, starts with a C, meaning I'm going to write this as a cosine. Now I can treat this as one giant fraction. I could rewrite it together and just kind of smush everything in the top together and smush everything in the denominator. Right? I can make this just one big fraction if I wanted, or you can just kind of cancel things out the way it is right now. But just to show you, we've got sine squared of x times the cosine of x in the numerator. In the denominator, I have a single sine of x times a cosine of x. Sometimes it's nicer to write it as one fraction so you can kind of see, all right, what do I have in the numerator and in the denominator that could possibly cancel out? And first thing that's easy, I see a cosine on the top and a cosine on the bottom. They both cancel. Again, you could have done that from this previous step. Just see a cosine up top somewhere with the cosine on the bottom somewhere. They would cancel. Now I've got sine squared divided by sine. Would all the sines cancel out, do you think? Just one of them, though, right? If I have 2 sines in the numerator, because sine squared, isn't this sine of x times a second sine of x? Like that's what sine squared actually is. It's a sine times a second sine. So I've got 2 sines in the numerator, only 1 in the denominator. So if I'm simplifying this, I know that one of the sines will cancel with the 1 sine in the denominator, but I still have this one left over. It would still be there. And so I still have a single sine of x. And there are no other trig functions anywhere else. Everything else canceled. No? Yeah? What'd you get? Whew, let's take a look. All right, so you
It was right there, and then we went like one like that.
sine squared, cotangent is 1 over tangent, 1 over cosine. All right, so 1 over tangent wouldn't be sine over cosine because tangent is sine over cosine, but it's the reciprocal of that.
That's right.
So it would be, 1 over sine over cosine, which would be cosine over sine, which is cotangent.
Alright.
Which then would leave you with this. So we'll say you had it. We'll say you're there. All right, so again, I could have also said, hey, take out one of those two signs with this sign, and we're still left with another sign. That second sign in the numerator is still there. All right, so that's working with squared trig functions. It could be a third, fourth, or fifth degree or whatever. All right, now we're going to learn some new identities. Absolutely, you're going to want to write these down. Definitely going to want to write these ones down. So we're going to create some brand new trig identities. And we're going to create them by using the Pythagorean theorem on the unit circle. Wait a minute, we're still using that thing? Still using the unit circle? What? Yep. Still using this wonderful creation called the unit circle. Do you remember when I first started the first quadrant of the unit circle? Remember when I drew that triangle on the circle and we talked about how like cosine is x and sine is y? That was like weeks ago. And essentially, we know that the cosine of an angle is like basically the x coordinate and the sine of an angle is basically the y coordinate. Do you remember something like that? Several weeks ago when we first started. So let's look at this right triangle here. And what if I set up, since this is a right triangle, I can use any of those properties of right triangles, such as the Pythagorean theorem. Now, for any given angle anywhere on this unit circle, I know that the x-coordinate is the cosine of that angle, and the y-coordinate would be the adjacent side would be the cosine of the angle, and the opposite side would be the sine of that angle. Those would represent the two legs of the right triangle. And what do we know the hypotenuse is on the unit circle? Always going to be 1, because that's what part of the circle? The middle. What's that middle line called on the circle? Radius. Yeah, the radius is 1 of the unit circle. So you know that that's a 1. You can see I've got that right here, right? This distance is 1 no matter where on the unit circle. So let's just take our Pythagorean theorem. A squared plus b squared equals c squared. But let's use these values from our unit circle. Oops. All right, so A and B. What do A and B have to be on our triangle? They have to be which sides? The two legs. What are my legs of this triangle on our unit circle? Sine and cosine, right? Does the order matter? Which one's first and second? Like that could be A, this could be B. Is that okay to do? The two legs are A and B. So instead of writing A squared plus B squared, what would I write? Yes, cosine squared plus sine squared. That's right. Cosine squared of, now remember, this theta, everybody, make a little note because that gave some students trouble on the test. This is called theta, and it's the same as just an x or a y or a z. It's just a variable. Whenever in math and science classes, whenever you're dealing with an unknown angle, standard protocol is to use Greek letters instead of our more familiar alphabet letters that we know. Some people thought that was a 0, and like for graphs, take like 2 pi divided by like 2 theta. People thought that was 20, and would like divide 2 pi by 20, and it got kind of crazy. So that's just your angle. That's the same thing as x, all right? So cosine squared of theta plus b is just the sine squared of theta equals c squared. Now c was always the hypotenuse. What is the hypotenuse of this triangle? It's just a 1, because that's the radius of the unit circle. It's 1 squared. Do I need to write that squared? Not really, right? 1 times 1 is just 1. So just using what we know about the unit circle and using the Pythagorean theorem, look at this. I've got a brand new identity. This will be true for any angle on the unit circle, meaning it's true for any angle at all that we create. Now, an identity is supposed to be a way that if I take a trig function or some combination of trig functions, I can simplify it to make it smaller. Look at the left side of this equal sign and compare it to the right side. Is one side a lot easier, a lot simpler than the other side? Yeah, imagine if you have to take this cosine of some angle and square it, then add the sine of that angle and square it as well. That's a lot of calculations you would have to do. But if you just see this pattern, I can just replace that, not even do the calculation, just say, oh no, that's going to be 1. I don't need to take my time with the calculations, which is crazy to think of. Cosine of an angle squared plus sine of an angle squared equals 1, but it does. It's the Pythagorean theorem right here, and you can do that for any angle at all. So this actually is our new identity. But there are 2 more identities that we can get from this, for a total of 3 Pythagorean identities. So what we can do is if I take each of these and divide by either a sine squared or divide everything by a cosine squared, we get 2 additional identities. Now here's what I mean. In algebra, if I divide one side of an equation by a value, I can divide the other side by that same value, and it still stays equal, right? We do that a lot to keep things balanced. So look at the left here. Cosine squared plus sine squared equals 1. That's the Pythagorean identity that we just kind of came up with. If I divide everything by sine squared, by sine squared, by sine squared. First off, am I allowed to do this algebraically? Is that a legal move? Dividing each term on both sides by the same quantity? Yeah, it's basic algebra. We can do that. If I do this, let's rewrite each of these 3 terms. First off, cosine squared over sine squared. What can I rewrite that as using some of our identities that we already know? That's the same as the cotangent of an angle. So I can say cotangent squared plus, how about this middle term? What's sine squared divided by sine squared? Good, that's just 1. Anything divided by itself equals 1. Finally, what's 1 over sine? That's one of those reciprocal identities. Do you remember which one it is? Switch the letter from an S to a C. That'd be cosecant. So if it's 1 over sine squared, we can say, oh, that's cosecant squared. Lo and behold, we have a brand new identity that relates different sets of trig functions. The cotangent of an angle squared plus 1 would be the same thing as the cosecant of that angle squared. So it's a way to simplify some of these expressions. This is our second Pythagorean identity then. And we can do a third by doing something very similar. I'm going to take that original Pythagorean identity, and I'm going to divide each of these by the cosine squared. Cosine squared, cosine squared, cosine squared. if I take that same Pythagorean identity that we got from unit circle, and I divide both sides by the cosecant squared of an angle, let's simplify this. What's cosine squared over cosine squared? It's just a 1. Plus sine squared over cosine squared. Well, what's sine divided by cosine? I can replace that with just a tangent. And finally, equals on the right side 1 over cosine. That's one of our reciprocal identities. That's just the secant. Yeah. And that's another identity that we can use to simplify expressions. If you see 1 plus the tangent squared of an angle, instead of doing that, I can just simply take the secant squared of that angle. So you don't need to know how we got these, but I wanted to show you in case you do forget them, they're very easy to recreate. The one that you do want to keep in your mind is that Pythagorean identity, which is pretty straightforward. You know, cosine squared plus sine squared equals 1. These other two are created simply by dividing everything by either a sine squared and simplifying, or by dividing everything by a cosine squared and then just simplifying. So these are your 3 Pythagorean identities. And these are the last identities that you're going to be learning this year, okay? So we've got those reciprocal identities, the quotient identities that are for tangent and cotangent, and now you have these 3 Pythagorean identities. You should have all of these somewhere in your notes boxed up really nice and neatly because you're going to be referring to them a lot throughout this entire week. You're going to need to refer to them somewhere. You need to make sure that you've got these written down nice and cleanly somewhere. Easy to understand. So these ones are a bit different, a bit new. But you want to look for them because it does simplify things, especially if you've got multiple terms. If you're adding or subtracting something, maybe you can use one of these identities to get rid of that. Instead of having 2 terms, we now just have 1 term. Much simpler. All right, I'll give you another moment to write these all down nice and cleanly. Did you write these down? I've been saying that for the last 3 minutes. How important it is to have these written down very clearly somewhere. So the reason I showed you that original diagram with the unit circle and then calculating them by dividing by sine squared or by cosine squared is simply because I'm showing you that you don't have to memorize these. You can just recreate them pretty simply. That's why I went through that in the lesson. But on like a test, the question always comes up, Wojcik, do I need to know this for the test? Are you going to give this to us? And no, I'm not. These are just relationships that you should understand from these basic principles of trigonometry. All right, I just demonstrated how we can create those with basic skills that you've learned several years ago. And again, just like everything this year, the more we practice them, the more we use them, the easier they're going to be. Easier to remember, easier to use, easier to substitute things. So let's look at how we can use these to simplify some of our expressions. First off, how do you know when to use one of these? Okay, before I had told you that you should always rewrite things in terms of sine and cosine. And so you might see this tangent squared and say, oh, right away, I know that's sine squared over cosine squared. But then you got this plus 1, and we don't have an identity that looks like that. We don't have an identity that says sine squared over cosine squared plus 1. So you want to pump the brakes a little bit if you do see something not written as sine or cosine. If you notice there's a trig function squared anywhere, that should be your first indicator to be like, okay, wait a minute, before I replace these right away, could there be a Pythagorean identity? And that's where you want to look for something else being like added or subtracted. Typically a 1, a plus 1 or a minus 1, but it also might be a second trig function. Like that first Pythagorean identity is the cosine squared plus the sine squared. So if you see that, you want to try to recognize this. So if you see a squared function and then something being added or subtracted, I want you to think, okay, wait, before I just replace things with sine and cosines, let's first see if is there a Pythagorean identity with these terms in it that I could use to replace it. And so right here, I see a tangent squared plus 1. So I'm not going to go ahead and substitute the tangent with sine over cosine. I'm going to think, wait a minute, is there a Pythagorean identity that looks like this, that has a tangent squared and a 1 in it? And I go back to my list, and I see, let's see, a tangent squared and a plus 1. Do we have that somewhere? Yeah, if you look down here, here's a tangent squared plus 1. It's written the other way, though, 1 plus tangent squared. Do you think that makes a difference? No, not for adding these. These are just numbers. I can switch the order around. So 1 plus tangent squared is the same as tangent squared plus 1. And what is 1 plus the tangent squared? It's just the secant squared. So let's go back to this problem right here. If I see the tangent squared of something plus 1, I know that that actually just equals the secant squared of the angle. And then we're done. I have a single trig function. I don't have a denominator, right? That's kind of a way that you know that you've reached the end. Because I could write that as 1 over cosine squared, but that's now adding in more calculations. You're adding in an additional fraction. This is our goal, to try to get to a single trig function if we can. So secant squared of x. Try this one. 1 over the cosecant squared plus the cosine squared. Simplify that to a single trig function. Now that looks really weird. I haven't done anything with like adding fractions together. Oh, you think you've got it?
I just had a question.
Oh, okay.
So, I don't have it written down yet, but when you
Yeah.
flip, the first one over,
Yeah.
and then it's like this one,
Yeah, that's right.
but then there's no one.
No, because it would be just the numerator. So you're taking 1 over.
Oh, I know
It would just be what?
this one right here. There's no one.
Oh my gosh. But you would have the left side, wouldn't you?
Mhm.
And you're trying to see, hey, what does that equal?
What equals
So
one?
if you have this plus this, what can you write it as? Well, we can rewrite it. It's just that. Do you want to maybe write some of those steps down so you kind of remember this when you're doing homework or reviewing or things like that? Because if you just see a 1 in your notebook circled, that's going to mean nothing to you, right? Yes. Yes. What can you rewrite this as? Yes. So it's not, since this is already 1 over, if we look at our reciprocal identities, 1 over the cosecant, 1 over the cosecant is just that. It wouldn't be 1 over it because it's already got that 1 over, right? You would flip it and change it to what it's equal to. Keep going. Yeah. Squared still, right? Because it's got the square. Plus cosine squared. Done. So see you've got these two things that are squared right here, and they're being added. So you might think, okay, a Pythagorean identity, these are these new ones that we're just learning about. But none of these Pythagorean identities have fractions in them. So how can I get rid of this fraction? 1 over the cosecant is the same as which other just regular function that's not in a fraction form? Look at your reciprocal identities. Oh yeah, you got those. Yeah. Do you see 1 over cosecant anywhere? That's right.
Oh, so this,
All right, so hopefully the way that I would think about this if I saw this problem is right away I'm seeing addition and I'm seeing squared functions. So I do want to think, okay, these new Pythagorean identities, they're probably going to come into play here because that deals with adding or subtracting squared trig functions. And I don't have any trig function that has a fraction in it, right? These Pythagorean identities, if we look at them, none of these have fractions. So first thing, let's see, can I get rid of this fraction here? Can I get rid of that denominator? 1 over cosecant squared. How can I rewrite that as just a single trig function that's not in the denominator? Well, since I want to basically flip it, I should be thinking reciprocals. So what reciprocal identity can I use? 1 over cosecant is the same as which regular trig function? Just sine. And so we're going to write this. Yeah, that's what you said, right? That's the same as just the sine squared. Okay, 1 over cosecant is just the sine. And I still have this plus cosine squared. All right, so now let's take a look at our Pythagorean identities, because now I don't have any fractions. I just have 2 trig functions being added and squared. And if you look at your Pythagorean identities, do I have something with a sine squared and a cosine squared? Sure do. I see right here, hey, cosine squared plus sine squared, what is that equal to? Well, it's equal to just a 1. Well, that's awesome. That means I can just write this whole thing as 1. Is that simplified at all? I can't really simplify any more than that, right? A 1 is probably as simple as it gets. Dun, dun, dun. Any questions? So I know that this may be confusing and daunting, and that's because this is kind of like something brand new, and there's no direct way. You're not going to know, oh, first, I always do this. Well, not always. Remember when I said at the beginning of this lesson, hey, typically you can write things in terms of sine and cosine first, but that's not always the case, right? You might look for some of these squareds and addition or subtraction, and it might be a little bit different. Now, something else that can occur is they won't always exactly match a Pythagorean identity. You know, that one that we just did, that was nice. Sine squared or cosine squared plus sine squared equals 1. That was our first Pythagorean identity. It was a perfect match. What about this one? 1 minus the cosine squared. Now, this is not one of our Pythagorean identities because all those Pythagorean identities dealt with addition, and this has subtraction in it. So that might be confusing, like, oh no, are there a new set of identities with subtraction? Well, no, we can just use those same 3. But if I saw this problem right here, my first thought, again, okay, what if I write in terms of sine and cosine? No, this is cosine already. What about squareds and adding or subtracting? Yes. So I should still be thinking Pythagorean identities because I see that this is being squared and there's like a plus 1 or a minus 1 in this case. So I'm still thinking, okay, this looks similar, it looks close to something that could be considered a Pythagorean identity. And what I would do is kind of separately over here is rewrite what is the Pythagorean identity that deals with a cosine squared and a 1. And just write that identity out, like to the side. Cosine squared plus sine squared equals 1. That's our main identity, right? Our first Pythagorean identity that I've written in green. And I know that this identity has a 1 in it, and it has a cosine squared in it. But it doesn't quite look like this on the left. It's a little bit different. Well, the nice thing that I can do with these identities over on the right is they hold true with basic algebraic rules, meaning I can kind of rearrange it and move terms from one side to the other, and the identity will still be true. So I look on the left, I see a 1 minus cosine squared. On the right, how could I change this to make it look like a 1 minus cosine squared? What could I do to both sides of this equal sign to make it look like a 1 minus cosine squared? Any suggestions? I notice that this 1 is positive and that 1 is positive, so I'm probably not going to move the 1. But I see that this cosine squared is negative, so I've got a 1 minus cosine squared. So on the right side, what if I took this first identity and I subtracted a cosine squared from both sides? I'm allowed to do this to these identities because these identities are essentially equivalent equations. They're always true. They're identities. If I did that, then these would cancel out, and I'd be left with simply a sine squared equals. Now on the right side, I had a 1, and then I subtracted a cosine squared. So 1 minus a cosine squared of x. So this right here is still the same Pythagorean identity. I just rearranged one of those terms by moving it over. It's still that Pythagorean identity. But now look at the left side. Look at my original problem. I'm trying to simplify 1 minus cosine squared of x. Do I know what that's actually equal to now? Yeah, look at this. Isn't that exactly what's written here? And this is just a different way. This is just rewriting that first identity. I see that 1 minus cosine squared is the same as just a sine squared. So over here, this 1 minus cosine squared, I can rewrite that as simply a sine squared of x. So that's still using that same Pythagorean identity. I just had to rearrange some terms. So you are allowed to rearrange those identities to kind of make it match up with whatever you've got, whatever you're using. Try this one on your own. This will be our last one for today. Cotangent squared. Now look, I used a new variable y. It's the same as x, same as theta. I want you to get used to seeing different variables in there. So if you've got the cotangent squared of an angle and you're subtracting the cosecant squared of that same angle, what would that be? And so right off the bat, we should be thinking Pythagorean identities because I see two trig functions being squared and I see a subtraction sign, but I know it's not going to perfectly match one of our Pythagorean identities. So what I would do is take the one Pythagorean identity that uses cotangent and cosecant and see if you can rearrange the terms in that identity to make it look just like this, with a positive cotangent squared minus a cosecant squared. Can you rearrange them to make it look like this? And once you do, once you get that match, you can simply write what this equals. Yeah. What? What? Yes, that's the right identity. How can you rearrange these to make it look like this? Yes. Yes. Oh. It really is a skill that you just have to mess around with things, try things, and you have to be okay with taking a leap of faith and failing and then starting over and trying again. Kind of like if you're solving a maze, you get to a dead end, you don't just quit, right? You go back and you try something else. Does that work? No. Go back, try something else. What do you think?
It's just a secant, right?
Nope.
Normal tangent is cosine over sine.
That's right.
Sine is sine over cosine.
Well, no, that's cotangent right there. That would be cosine over sine.
Yeah, that's what I meant. And then for oh, that's not cosine. That's cosecant.
Mm-hmm. Which is 1 over sine.
Yeah. And the two sines cancel. It's just easy with cotangent.
So first, let's look at our Pythagorean identities. And there's one of them that does have a cosecant squared and a cotangent squared. So that's the one that we're going to be using. I see this right here. Cotangent squared plus 1 equals cosecant squared. All right, so that was cotangent plus 1. So cotangent squared plus 1 equals cosecant squared. So on the right side, this is just the identity. And I'm going to try to rearrange it to make it look like that on the left. Now on the left, I notice that cotangent, this is a positive cotangent. And so if I look at my identity, I see, hey, that's also a positive cotangent. So I'm going to leave that the way it is. Right, I'm going to leave that cotangent on the left side. I'm not going to change it because it's already positive. I want it to be positive. But then I notice that I've got a minus cosecant squared. So this cosecant squared that's on the right, that's positive, I'm going to subtract it because I want it to be subtracted from the cotangent squared. So that's what I'm going to do first. I'm going to subtract this cosecant squared minus cosecant squared of x. Because now when I write this out, I can say, hey, this is the cotangent squared of x minus the cosecant squared of x. And that's kind of what I wanted there. Unfortunately, I still have this plus 1. And now this equals 0, right? Because cosecant squared minus cosecant squared is a 0. So this is really close at this point because I see cotangent squared minus cosecant squared. Cotangent squared minus cosecant squared. It's really, really close, except there's this plus 1. Got to get rid of that by simply subtracting 1. Hey, everybody. And so then I can see that the cotangent squared minus the cosecant squared equals a negative 1. Now I've got my substitution. I see that, hey, this whole piece is this whole piece, and that equals a negative 1. So this right here just equals a negative 1. Simply by rearranging those identities. Whoa. So you're going to start recognizing these just by practicing, by playing around, by manipulating, trying, and being okay with failing. Even if you try something different. The thing with these identities is there's often more than one way to solve these problems. Take a look at this. What if I rewrite this as cosine squared over sine squared minus 1 over sine squared? I have two fractions. And what you notice is true about those two fractions, denominators. They're the same. What can I do if I've got two fractions with the same denominator? common denominator. I could write this as just sine squared of y. In my numerator, I've got cosine squared minus 1. Cosine squared minus 1. Using one of your identities. Look here, cosine squared minus 1. So if I took this 1 and I subtracted it, I'd have to take this sine and subtract it. And there I've got cosine squared minus 1 equals a negative sine squared. So I can write this as simply negative sine squared over positive sine squared. Hey, what's negative sine squared divided by positive sine squared? A negative 1. And you get the same thing. So there's multiple paths that you could take, but you're always going to get the same answer at the end. Now, everything you try won't always work out nicely like this. But for the most part, the more of these you do, the easier they get. So guess what I have for you all now? Delta math. What? Is it unlocked? Let's take a look. Trig identities. Yeah, we'll open that up right now for you. So you're practicing just 2 of these identities. You have 8 questions in each, but they're very simple, very straightforward. Let's start with the Pythagorean. A single trig function with no denominator. Secant squared minus 1. So again, I'm going to look at my identities here. Ooh, I want to make that a little smaller. And secant squared minus 1. I look up here, and I'm looking for a function or identity with a secant squared and a 1. Well, that'd be right here at the bottom. You can see that I've got a secant squared, just like this secant squared, but it's being subtracted by 1. So if I took this 1 and I subtracted it, I'd subtract it over here. And now I have a secant squared minus 1. And what's it equal? What's left over on the left side? Well, just a tangent squared. So that's going to be my answer that I can type in. Now to type these in, tangent squared, I can use my shortcuts. Tangent, I'm going to do shift 6 to give me that little exponent. Squared, press the right arrow key to drop down to the regular level, and then hit X. So that's the same as the tangent squared of X. So these ones are very straightforward, just helping you relate those identities. You are going to have to do some rearranging for some of them. What about this one? What's sine squared plus cosine squared? Sine squared plus cosine squared, that's the easiest one. That's our basic Pythagorean identity. That's just going to be a 1. Right? Others, you're going to just do some rearranging from one side to the next. The other skill, the reciprocal trig identities. So these ones, notice there's nothing being added or subtracted. And so I'm not going to worry about the Pythagorean identities. I'm going to use those reciprocal identities or those quotient identities. And this is where you want to try writing everything in terms of sine and cosine. And so I already see a sine on the bottom. Up top, I see a cosecant. And so I would start by rewriting cosecant in terms of sine as 1 over sine. So to have 1 over sine divided by another sine. So you're dividing by 2 sines. That'd be 1 over sine squared. 1 over sine squared. Last thing is the reciprocal of sine is cosecant. So you can write that as cosecant squared. And then to do theta, you can just click on that right there. Boom. All right, so take the next 5 or 6 minutes and start working through these.